Welcome to this first lecture in EE 557. In the last lecture, we have seen some facts about asymptotic properties related to linear algebra, and we have also seen the convergence of mean when A is a stable matrix. In this lecture, we're going to try to concentrate on the covariance. So let us remember our system. I'm writing this over and over. I have A xk plus B uk plus GWK, and I have YK. We are not interested in the output equation nowadays. So I have also HVK here. Remember, we assumed X0, W0, W1, and V0, V1 are independent. That means that in order to be able to write a joint distribution, we need to know only the marginal distributions. And the marginal distributions of these variables are all Gaussian, and X0 is distributed as normal X0 with mean X0 bar, and I have here covariance sigma 0. WK, they are also Gaussian with mean 0 with covariance Q, and VK, they are normal with 0 mean and covariance R. Okay? And we have defined the mean xk bar as the expected value of xk, and we have also defined the covariance sigma k, which is the covariance of xk, meaning that expected value xk minus xk bar, xk minus xk bar transpose. Okay? And remember, we have found explicit expressions for both the mean and the expected value. Remember, the mean propagates as follows. So mean actually can be given as follows. So I have a to the k times x0 bar plus I from 0 to k minus 1. I have a to the k minus 1 minus I times b times uk. Okay? This is the explicit expression that we have found for the mean of the state. And we have also found the explicit expression for the covariance. Sigma k is ak, sigma 0, a to the k transpose. And I have plus, again I from 0 to k minus 1, a to the k minus 1 minus I. I have this, in this case, GQ G transpose, a to the k minus 1 minus I transpose. Here, any power operation of a matrix can be interchanged with the transpose. So this is at the same time a transpose to the power k minus 1 minus I. So these were the explicit formula for this mean and the covariance. We have also found the recursive formula for this. I have xk plus 1 bar is equal to axk bar plus buk. And for the covariance, we have sigma k plus 1 is equal to, I have a sigma k, a transpose plus gq g transpose. Okay? So we have these recursive expressions. Now we are interested, remember in the last lecture we were interested in what happens to the limit as k goes to infinity xk bar. What happens to the mean as k goes to infinity? And we have seen that if a is stable, and if this uk is a constant input, then this xk goes to a constant xk x infinity bar. Okay? And it remains there after converging to that value. In this lecture, we are going to be concerned with limit as k goes to infinity sigma k. Okay? We are going to be interested in this limit. All right? So before actually starting with this topic, I would like to examine a simple example here. Example is going to consider the scalar case. Okay? So the scalar system is given as xk plus 1 is equal to axk plus buk plus g I have wk. In this case, the matrices are scalars. That is why I show them with small letters here. And I'm assuming that A is greater than or equal to 0. B is not equal to 0, so that the system actually has an input, effective input. And I have G not equal to 0. Okay? So here I'm assuming that x0 is distributed with, normally with mean 1 and the variance 4. And I have, let us say, wk is distributed as with 0 mean and the variance q. And here I'm of course assuming that q variance is a positive number. And finally I'm assuming that uk is equal to uk bar, which is non-zero. All right? So these are my assumptions, and this is the model that I need to consider. And now what I need to do is to find these limits. What is limit as k goes to infinity xk bar, and what is limit as k goes to infinity sigma k. In this case, I'm showing the variance of the state with small sigma. Okay? Because it's a scalar, it's not a matrix anymore. I show it with small sigma k. Here, I'm not using square for the variance. That you should be careful about that. So here, what is this variance? All right? So I can actually write here, sigma k is nothing but the variance of xk. The first thing that I'm going to do is to write these expressions. Let us first concentrate on the mean limit. So I have this expression. Let us write the scalar counterpart. So I have xk bar is equal to, I have scalar a to the k times x0 bar. X0 bar here is 1. So I would leave this as it is, because x0 bar is just 1 here, plus I would have I from 0 to k minus 1, I have a to the scalar a to the power k minus 1 minus I, and I have b, and I have the input is independent of the time instant. Actually here you see there is a mistake. This is not going to be k, it's going to be bui. Okay? So here it is not going to be ui anymore, because ui is equal to u bar for all time instants. So this bu can be taken outside the summation. So let us try to continue with this expression, a to the k. Now I'm going to take bu outside, bu bar, and I have I from 0 to k minus 1, a to the k minus 1 minus I. Now I want to take the limit as k goes to infinity. And you see here that this a is non-negative, and I'm going to take the limit as k goes to infinity. I can take this limit quite easily, but this limit looks more challenging, because k appears both in the limits of the summation and in the power of a in the argument of the summation. So I want to get rid of this k in the argument. That is why I'm going to make a summation variable change here. Let us say that I prime is k minus 1 minus I. Then I can write this summation as follows. I prime from when I is equal to 0, I prime is k minus 1. And when I is equal to k minus 1, I prime is 0. And I have a to the I prime. Okay? You see that this summation really gets into a much simpler form. But here, instead of I prime, I can write just I. And the order of the limits of the summation really does not matter. That means that I can write I from 0 to k minus 1, a to the I. Okay? So now I can use this result, that is a to the k, so let us say that this is separate, a to the k plus bu here, and I can write the result of such a summation. So that is just a geometric series. So I have I from 0 to k minus 1, a to the I. This has an explicit result when a is not equal to 1. When a is not equal to 1, then we have this one as 1 minus a to the k divided by 1 minus a. And I have also when a is equal to 1, this is quite easily seen to be just k. Okay? So this is the geometric series result. Then I can use this result here. All right? So I'm just going to write 1 minus a to the k over 1 minus a when a is equal to 1. And here a is not equal to 1. And when this is k when a is equal to 1. Okay. Now I'm actually, so this is xk bar. All right? Now I can actually try to take the limit. Let us write x infinity bar is equal to, I'm considering only non-negative a values. So a can be 0 or a positive number. So I want you to think about the negative values of a as an exercise. All right? So, but here I'm only going to consider the non-negative a values. So here we see that if actually I have, let us say, a is greater than or equal to 1. In that case, what happens? Let us first say a is strictly larger than 1. When a is strictly larger than 1, then I know that this, when I let k go to infinity here, this number is going to diverge. That means that x infinity is going to diverge. That means that x infinity bar is going to be infinity when a is strictly larger than 1. Similarly, you see here that if a is exactly equal to 1, if a is exactly equal to 1, then I need to use this result. And you see that if a is equal to 1, this term is finite. It is always 1. But you see that bu times k is going to diverge. Here, I know that bu times, this is u bar by the way, bu bar times k is going to diverge because b is non-zero and u bar is non-zero. That means that b times u bar times k is going to go to infinity. Okay? So that means that for all, when a strictly larger than 1 and when a is exactly equal to 1, this result is going to infinity. All right? Sometimes this result, this means that this limit doesn't exist. So infinity is one case. If a was equal to minus 1, in that case, what would happen? In that case, you might see that here, I would see that this summation would not converge, and this would not converge either. Okay? But you see that both of these terms, when a is equal to minus 1, both of these terms would be actually finite. Okay? In that case, I cannot write here infinity. But what should I write? I need to write does not exist. Okay? So instead of infinity, I can write does not exist. But instead of non-converging result, but not going to infinity, I need to write does not exist, not infinity. So when a is equal to minus 1, instead of infinity, I need to write does not exist. Okay? But infinity is also one of the cases when the limit does not exist. So now let us look at the case when a is strictly smaller than 1, and we are considering here a larger than or equal to 0. When I have this case, this number is going to go to 0, And I see that this a to the k is going to go to 0, so this is going to turn into 1 over 1 minus a, and I would have bu bar. Bu bar 1 minus a. Okay? So this is the result for x bar infinity. And remember here our result. Actually, we have seen that in the case when a is stable, in that case, I can take the limit of this recursion as k goes to infinity, and I can write that x infinity bar is equal to a times x infinity bar plus bu bar. Okay, so in this case uk is constant u bar, so I change it with u bar and I let k go to infinity, and in that case, assuming that x infinity exists, in that case I see that we need to satisfy this equation. Okay, so I see here that when a is stable, in the case of a scalar, stability of the matrix A turns into the result of absolute value of A being smaller than 1. Okay? And you see that in this second case here corresponds to the case when A is stable. All right? In that case, I see that the limit is finite and constant with respect to k. And it is also, you see also that it is the solution of this equation for x infinity. Because if I try to solve this equation for x bar infinity, then I see that the solution is bu bar times 1 minus a. Okay? So this confirms our theory for the scalar case. But I see here that if a is equal to 1, or if it is larger, then I see that the result is going to be infinity. Okay? Does this always have to be the case? If a is strictly larger than 1, then do you think the mean is always going to go to infinity? If a is strictly larger than 1, or if it is equal to 1, do you think x infinity bar is always going to go to infinity? The answer is no. Our theorem that we have seen for the mean tells us this. If a is stable, then we have seen that x infinity bar is going to be the matrix version of that result, I minus a inverse bu bar. Okay? That was our theorem. Okay? So what can we say when a is not stable? If a has eigenvalues with magnitude exactly equal to 1 or strictly larger than 1. In this case, this theorem doesn't tell us anything. Okay? Because the condition of this is not a double implication. This is a single-sided implication. And when a is not stable, it really doesn't tell us anything about the convergence of the mean. The mean can converge, or it might not converge, and it depends on the parameters of the system. Consider the following system: xk plus 1 is equal to 2xk plus I have here, let us say, b times uk. Okay? So that is my system, and in this case I am assuming that b is equal to 0. Okay? In that case, and suppose here that x0 bar is equal to normal 0, 1. Okay? In that case, what is the mean? Does the mean converge? Does the mean converge to a stationary value? In that case, the answer is going to be yes. Here, x0 bar is going to be equal to 0 because of this mean here. And if b is equal to 0, the input values will not matter, and the mean is going to evolve with this equation, xk bar. Okay? But you see that if x0 bar is equal to 0, xk bar is going to be equal to 0 as well. So you see that in this case, xk bar x infinity bar is equal to 0. Okay? It converges to a finite value, and we see that A is not stable because I have a 1 by 1 matrix and its eigenvalue is itself, which is equal to 2, which is outside the unit circle. That means that we have an unstable system, but we have convergence. So you see here that our theorem really does not tell us that when A is not stable, X doesn't converge. It is only for this example that this happens. Okay? We see that is possible, all right? But for this example, you see that a infinity bar can be finite, and xk bar can converge to a finite value. Okay? So do not misinterpret the theorem. When A is not stable, the theorem doesn't tell us anything about the convergence or the limiting value of xk bar. All right? But for this example, when A is not stable, you see that the xk bar really does not converge. All right? So now let us go into the case of covariance. I will leave this part. Maybe I shouldn't have erased those. So here I have x0, here I have wk, q is larger than 0, and there was something else here. So here I define sigma k is equal to variance of xk, and we know the explicit equation for that sigma k. Sigma k is going to be a to the power k times sigma 0. We see that sigma 0 is 4 here. Okay? So this is 4, and I have a to the k again. In this case, transpose doesn't have any effect on the scalar, so I have again a to the k. And I have plus, I have I from 0 to k minus 1, a to the k minus 1 minus I. I have GQG transpose. G is now a scalar, and Q is a scalar, so I have G squared Q here. All right? And finally, I have a to the k minus 1 minus I. All right? So now this is equal to 4 times, I will write this is a to the 2k, I will write this as a squared to the power k, okay? Which is the same thing, plus I can take g squared q outside, g squared q out, so I have I from 0 to k minus 1. This is going to be a to the power 2 times this power here. I will write it as a squared to the k minus 1 minus I. Okay? This is equal to 4a squared to the power k, and I have plus g squared q. Here, let us change the summation variable once more. This is going to be I from 0 to k minus 1, a squared to the power I. Okay? Now I'm ready actually to write my final result with the result of this summation. That is going to be 4a squared to the power k plus g squared q, and this summation is again the geometric series. In this case, instead of a, I have a squared, and that is going to be 1 minus a squared to the power k over 1 minus a, when a squared is equal to 1, and when a squared is not equal to 1, and I have when a squared is equal to 1, this is going to be equal to 1. So I have k, the result of the sum, as a result of the summation. Now I can let k go to infinity. This is sigma k. In this case, our sigma infinity is going to be I'm again going to have two cases. So if I have A is larger, if it is strictly larger than 1, then you see that this is going to diverge. Okay? And if A is exactly equal to 1, then you can see that this K is going to diverge. And therefore, for A larger than or equal to 1, I would have infinity. So sigma infinity does not exist when A is larger than or equal to 1. Okay? And what about the case when A is between 0 and 1? In this case, this is going to go to 0, and this is going to go to 1 over 1 minus A. So I have G squared Q over 1 minus A as my limiting result. So you see here again that if A is stable, we have a finite covariance and finite stationary covariance. The covariance converges to a constant value. We get a stationary covariance as K goes to infinity. And remember that here we didn't write it, but here if I assume that sigma K converges, then I can actually write the following. Sigma infinity is equal to A times, this is going to be sigma infinity, and this is going to go to sigma infinity. When sigma infinity exists, then I can write this here. I can let K go to infinity on both sides of this equation, and that is going to give me the equation sigma infinity is equal to A times sigma infinity times A transpose plus GQ G transpose. But in the scalar case, I would have A squared sigma infinity, and I would have plus G squared Q. Okay? And you see that if you solve this equation for sigma infinity for the convergent cases, when A is strictly smaller than 1, in that case you would get the same result here. So sigma infinity is the solution of this equation. G squared Q over 1 minus A. This is going to be A squared. This is going to be A squared. I'm sorry, I'm making really lots of mistakes here. So here, the argument of the geometric series was A squared. That is why instead of A, I need to substitute A squared. That is going to be 1 minus A squared to the power K and 1 minus A squared. Okay? It is still good that I have an autocorrection mechanism here. So that actually completes this example, and in both cases we have seen the same thing. When A is stable, when the matrix A is stable, or in the scalar case, when the magnitude of the scalar is strictly smaller than 1, when we are in the unit circle or in the unit interval, in the scalar case, the mean converges to a stationary value plus the covariance converges to a stationary value. Okay? Now we are actually ready to investigate this. We have already investigated the stationary mean case, and now we are going to investigate this stationary covariance case. Okay? Well, let me erase this part. So the first thing that I'm going to do is to change this formula. We are going to investigate the covariance, the limiting value of the covariance. And as a result, the first thing that I'm going to do is to change this formula a little bit. Here you see that when we are trying to calculate in the scalar example, we were always making a summation variable change and writing the summation variable I prime is equal to K minus 1 minus I, and then we get rid of these k's in the arguments of the summation. We really do not like this because we would like to let k go to infinity, and I don't want an infinity here inside the summation. Okay? So that is why we are going to make a summation variable change here there first. So sigma k is going to be a to the k, sigma 0, a to the k transpose, or a to the transpose k to the power k, plus if I make that summation variable change here, this is going to be I from 0 to k minus 1. So you just do that summation variable change, you're going to get this, a to the I, GQG transpose, a to the I transpose. Okay? So now with this formula, we are ready for our stationary covariance result. Let us say theorem. Let A be stable, okay? Then there is a positive semi-definite matrix, sigma infinity, such that limit as k goes to infinity, sigma k is equal to sigma infinity, okay? Moreover, sigma infinity is the unique solution of the linear equation that is linear in sigma infinity, and that equation is given as sigma infinity is equal to A sigma infinity A transpose plus GQ G transpose. Okay? So this is our theorem, and we're going to spend some time in proving this. So we see here that the theory tells the same thing as the theorem for the stationary mean case. If A is stable, meaning that all of the eigenvalues of A are in the unit circle, then this sigma k, or this recursion, it converges. And it converges to a positive semi-definite matrix sigma infinity. Okay? And the theorem tells us also that this sigma infinity is going to be a solution of this equation. Actually, it is really very simple to see this. Just if we know that sigma infinity exists, just let k go to infinity in the second equation. You see that sigma infinity is A times sigma infinity A transpose plus GQG transpose. So we see that sigma infinity is always going to be a solution of this equation, but the theorem claims more. It says that this is going to be the unique solution of this equation. So such an equation can have multiple solutions at the same time. That means that in this stable A matrix case, we have a very good property that if I try to solve this equation for sigma infinity when A is stable, I'm going to get one and only one solution, which is going to be the positive semi-definite matrix sigma infinity. Okay? So really, I do not have to take this limit then, and then I can try to solve this equation instead. So here, I'm going to take the limit as k goes to infinity of both sides here. So here we have said that A is stable. If A is stable, we know that A to the k goes to 0 n by n, if A is stable. Okay? And what do we also know when A is stable? A to the k decays as I have maximum over all i's, absolute value of lambda i's to the power k. I know that all eigenvalues of A are actually in the unit circle. That means that this number is smaller than 1. So we see that a to the k decays like a geometric series. Okay? That means that this summation also converges as k goes to infinity. Okay? Because here I have a matrix with decaying elements like the geometric series, and I have another matrix whose elements would decay as this geometric series, and I have constant matrices, but they really do not matter. I can have any constant here. So here, since A is stable, I will write here, since A is stable, in this case I have the first result as a to the k is going to go to 0 n by n, and I have the second result just this, and from this second result I can say that limit as k goes to infinity, I from 0 to k minus 1, a to the I, gq g transpose, a to the I transpose is going to exist. So this summation is going to converge to a finite series, and it's going to be I from 0 to infinity, a to the I, gq g transpose, a to the I transpose. Of course, if when k goes to infinity, if the summation does not exist, then I cannot write such an equality. It would be meaningless. And this should be infinity, or it wouldn't exist in that case. Okay? So here I see that when I take the limit of both sides here in this equation, these a to the k's are going to go to 0, meaning that this term is going to disappear. The effect of the initial covariance will disappear. The system is going to forget its initial covariance, and this summation is going to converge to this series. All right? So I see here that when A is stable, we are going to have sigma infinity is equal to I from 0 to infinity. I will write the same thing. A to the I, gq transpose, a to the I transpose. So this is our sigma infinity solution, but it is still in an abstract form, but we know that there exists such a sigma infinity matrix when A is stable. So here, so far, we have proven that there is a matrix sigma infinity such that we have this. Now let us try to show that this matrix is positive semi-definite. So in that case, I'm going to have just this. So I know that the matrix Q is larger than or equal to 0. I know that Q is a positive semi-definite matrix in general. Because Q is a covariance matrix, that means that it should be positive semi-definite. And at least positive semi-definite. And I know that for any matrix M, if I have a positive semi-definite Q matrix, for any matrix M, the matrix M, Q, M transpose is going to be positive semi-definite as well. Okay? This was one of the facts that we have seen at the beginning of this chapter. But here, these matrices are nothing but the matrices in this form. Q, a matrix M, times that matrix transpose. Okay? So each of these matrices, A to the I, GQ, G transpose, A to the I transpose, they are positive semi-definite matrices. All right? And when we sum positive semi-definite matrices, we need to always get positive semi-definite matrices. Okay? That means that since this is true for all I, and that means that sigma infinity should be positive semi-definite. Okay? So far we have proven there is a positive semi-definite matrix sigma infinity such that this one. So now we come to the second statement. Moreover, sigma infinity is a unique solution of the equation given like this one. I will first try to show that this sigma infinity is a solution of this equation. Okay? Actually, it has to be. Okay? Why? Because here I know that these covariances would satisfy such a recursion. If I let k go to infinity in this recursion, I would get just that result. So I have a limit k goes to infinity, sigma k plus 1 is equal to a limit k goes to infinity, sigma k, a transpose plus gq g transpose. If I know that sigma infinity exists, then I can write sigma infinity is equal to a sigma infinity, a transpose plus gq g transpose. Okay? So we see that this sigma infinity has to be a solution of that equation. So here, that is one proof that this solution has to satisfy that equation. This is an indirect proof. So I know that this equation has to be satisfied, and then I take limit as k goes to infinity. A direct proof, so I can have an alternative proof to that one. So instead of showing that this satisfies that equation like that, I can actually make a more direct proof. I can actually take this sigma infinity. Let us write it. Sigma infinity is equal to, I will separate the I equals to 0 term from this summation. So I will write I from, if I take the 0 term out, then I would have I from 1 to infinity, and I have a to the I, GQG transpose, a to the I transpose, plus the 0 term is going to be GQG transpose. Why? Because a to the power 0, when I substitute I equals to 0, is going to be identity, and this is going to be identity as well, so I would end up with GQG transpose. So I see that sigma infinity is going to be given by this expression. Now I take, so you see that here I have the a to the i's. I start from 1 to infinity. So I have here a square, a cube, etc. So now I can take a parentheses here. A from the left, I from 1 to infinity, a to the I minus 1, GQG transpose, a to the I, and from the right I can take a transpose parentheses. Okay, so that is going to be, this is going to be I minus 1 as well. And I have a transpose here plus GQG transpose. So I have taken a parenthesis from the left and a transpose parenthesis from the right. Remember, a to the I transpose is nothing but a transpose to the power I. So I can take one a transpose parenthesis there. So here I have in the middle, I have a term, and now let us make a summation variable change. I will change the summation variable into I prime is equal to I minus 1. Okay? In that case, when I is equal to 1, so this is A, and I have this term here, A transpose plus GQG transpose. And here I am going to write the summation in terms of I prime. When I is equal to 1, I minus 1 is equal to 0. So I prime is equal to 0. When I is infinity, I prime is infinity. And A to the, I have I prime, GQG transpose, A to the I prime transpose. Okay? But here I prime is not really significant. I can remove these primes from here. Okay? And you see that this is nothing but sigma infinity itself. That's sigma infinity. So I have here sigma infinity, which means, and here the left hand side was sigma infinity, and the right hand side is A sigma infinity A transpose plus GQG transpose. Okay? So we see here that we could prove directly that this solution should satisfy this equation. This is just an alternative proof to this easier one. Okay? So now, so far, we have shown that sigma infinity is a solution of this equation, okay? Sigma infinity is a solution of this equation. We have shown that. But still, there is one thing that we have not proven, and that is the adjective unique here, okay? You need to show that this thing should be the unique solution of that equation, okay? Let us try to do that. So you might remember from the course 501 that uniqueness proofs are always done by something called proof by contradiction, okay? And proof by contradiction always starts with the following assumption. Suppose that sigma infinity is not unique, okay? We are supposing that sigma infinity is not unique, and in that case, that means that I need to have two sigma infinities, sigma infinity 1 and sigma infinity 2, and I know that both of those sigma infinities should satisfy this equation, okay? Because I have shown that if sigma infinity exists, even if there are more than one sigma infinities, they need to satisfy this equation, okay? By the first proof. And in that case, that means that I need to have sigma infinity 1 is equal to A sigma infinity 1, A transpose, plus GQ G transpose, and sigma infinity 2 is equal to A sigma infinity 2, A transpose, plus GQ G transpose, okay? Now I'm going to, using both of these equations, I'm going to try to go to a contradiction. Contradiction that, sorry, these are not equal, of course. When sigma infinity is not unique, there should be at least two sigma infinities which are different from each other, and I would have both of them satisfying the same equation, okay? So we assume the non-uniqueness, and I have seen that they both need to satisfy this equation. Now I will try to go to a contradiction showing that these two should be actually equal, okay? That is going to be contradiction of the assumption that I started with. So now I'm going to subtract these equations from each other. And I would have sigma infinity 1 minus sigma infinity 2 is equal to, I can here do this subtraction by taking A and A transpose parentheses from left and from right. I would have A sigma infinity 1 minus sigma infinity 2, A transpose, and GQG transposes, they would cancel out from these equations. So you see that I have the difference matrix. I know that this difference should be non-zero because I assume that these two sigma infinities are different from each other. I will call this difference as the matrix delta, okay? Delta. And that is going to tell me delta is equal to A times delta times A transpose. Okay? We get just this equation. So now I can actually play with this equation a little bit. So delta is A times delta times A transpose. So I can write A, this is A times delta times A transpose. Instead of delta, I can just write this. A delta A transpose A transpose. But this is nothing but A square delta A transpose square, okay? Or A square transpose. So you see that delta is not only equal to A delta A transpose, but it is also equal to A square delta A transpose, okay? But I can continue with this logic. I can actually write, this is A square. Instead of delta, I can write A times delta times A transpose, and A times delta times A transpose A squared transpose. And this is going to be A cube delta A cube transpose. Okay. So you see that I can increase the power of A in that equation. So I can have delta is equal to, I would have A to the power K delta, and I would have A to the power K transpose. For any K, this is true. All right? But if this is true for any K, then that gives me the flexibility of letting K go to infinity. Now in this equation, let K go to infinity. The left-hand side is not dependent on K, so it remains as it is. But on the right-hand side, A to the K's are going to converge to 0. That means that the right-hand side is going to converge to 0. So if I let K go to infinity, it's going to give me delta is equal to 0 n by n. Okay? Which means that, which is a contradiction to the fact that sigma infinity is not unique. Okay? That means that the initial assumption cannot be correct, meaning that sigma infinity should be unique. Since I have already found a single solution of this equation, which was given earlier, which was just this thing. I from 0 to infinity, A to the I, GQG transpose A to the I. Since this is one solution, this should be unique. This is the only solution. And it is positive semi-definite. So we see that we have now completed our proof, and we see that when A is stable, we actually have the very similar property that the covariance of the state should converge to a stationary value. Okay? So I have some Gaussians in the states here. This is always going to give me Gaussian states. These Gaussians, they are actually, if A is stable, their means, and if U is constant, their mean is going to converge to a constant, and their covariance is going to converge to a constant. That means that the distribution of the state is going to converge to a constant distribution as K goes to infinity when A is stable. Okay? So this was our theorem. And actually, we are going to be able to improve this theorem just a little bit, adding an additional condition. So now I have some remarks. The equation sigma is equal to A sigma A transpose plus GQG transpose. This equation is called Lyapunov equation, is called discrete time Lyapunov equation in the control literature. This equation has a continuous time counterpart as well. If you have taken 502 from Professor Emre Tuna, then you might have seen that equation as well. So that equation looks like this: P times A transpose plus AP is equal to minus Q or something like that. Okay? This is continuous time Lyapunov equation, and this is the discrete version. Okay? That is the discrete time version of the Lyapunov equation. That is just some knowledge. And the next remark is about the theorem. Theorem says that, so the structure of the theorem is this. If A is stable, then sigma infinity exists. Okay? So there is an equivalent statement to this theorem. So this is like P implies Q, and the equivalent statement to, if I have a logic, I always talk about this in my courses. P implies Q type of implication is equivalent to Q complement implies P complement. Okay? But you need to be careful. These are equivalent, but these are not equivalent to Q implies P. Okay? So here, this statement is equivalent to, if sigma infinity does not exist, is the complement of this, Q complement implies P complement, then A is not stable. Okay? It tells us this. If sigma infinity does not exist, then for sure we need to have A, an unstable matrix. Its eigenvalues, there should be some eigenvalues of A, either exactly on the unit circle or outside the unit circle. Okay? That is what sigma infinity does not exist tells us with this theorem. Okay? But what can we say with the theorem for the case when A is not stable? Then does this imply that sigma infinity exists? Sigma infinity does not exist. Do we have such an implication with this theorem? So let us try to look at this. This is P complement implies Q complement. Okay? And it is equivalent to this one actually. Q implies P. Okay? So here, or can I ask the question, if sigma infinity exists, then can I say that A is stable? This is Q implies P. This is P complement implies Q complement, which is equivalent to this one. P complement implies Q complement. Okay? In general, our theorem tells us only these two. Okay? And the theorem does not tell us anything about such statements. Okay? When A is not stable, sigma infinity might exist or might not exist. I don't know based on this theorem. The theorem is not an if and only if theorem. So when it doesn't say anything about the case when A is not stable. When A is not stable, sometimes sigma infinity might exist and sometimes it might not. We will not know based on this theorem. Okay? Similarly, if sigma infinity exists, I really do not know if A would be stable or not. Okay? Theorem doesn't tell us anything about that. So I cannot say the reverse statement is correct in general. And actually I have an example for that. I have xk plus 1 is equal to, I have a two-dimensional xk plus 0, 0, 1 wk. Okay? And in this case, my A matrix is diagonal. I have 1 and 0.5, 0, 0. This is my A matrix, and this is my G matrix, the vector now. Now wk is normal with 0 mean and variance 1. Wk is just a scalar here. And here, therefore, this Q, or I can say this, since W is scalar, I can make this small q, but in order to remain consistent with this notation, I will say just Q is equal to 1. And let us say that sigma 0 is equal to the identity matrix 2 by 2 identity matrix. The task is to determine the sigma infinity if it exists. Determine sigma infinity if it exists. So I can really check if the conditions of our theorem would hold or not. In this case, what are the eigenvalues of our A matrix? We see that this A matrix is a diagonal matrix, and the eigenvalues of a diagonal matrix are its diagonal elements. I see that the eigenvalues of the matrix are lambda 1 is equal to 1 and lambda 2 is equal to 0.5. So you see that one of the eigenvalues is exactly on the unit circle. That means that sigma infinity does not exist? No, it doesn't mean that. It means that I cannot use my theorem. Okay? So here, I see that A is not stable, meaning that no conclusions using the theorem. Okay? So it just means A is not stable. It doesn't tell me anything about the existence of sigma infinity or not. So here we see that sigma k is going to be determined by these A to the k's and sigma 0 and A to the k's here. So let us try to calculate these matrices. So A to the ith power, a power of a diagonal matrix can be obtained as a diagonal matrix whose diagonal elements are the corresponding powers of the original diagonal elements here. So this is 1 to the power I, and I have 1 over to the power I here. Okay? So let me say that this is 1 over 2 to the power I. Okay? And it would, the other elements would be 0, 0. And what is GQ G transpose? GQ G transpose is, I have G is 0, 1, and Q is 1, and G transpose is 0, 1 like this. This matrix is nothing but 0, 1, and, 0, 0, and 0, 1. Okay? This is GQ G transpose. Now let us try to use our formula here. Maybe I need a larger space here. So let us use our formula. Sigma k. So can I use this recursion? Or can I use the sigma infinity is equal to A, sigma infinity A transpose plus GQG transpose? If some sigma infinity exists, it needs to satisfy this equation. Okay? So why not I just write sigma infinity A, B, C, D, some matrix with some elements, and then try to solve this equation. The reason that I'm not using this equation is that the solution really might not be unique. Okay? There might be infinitely many solutions of the Lyapunov equation when A is not stable. All right? If A is stable, I know that it has a unique solution, and this equation can be used to solve for sigma infinity when sigma infinity exists. Okay? Here, currently, I don't know if sigma infinity exists or not. That is why I really cannot try this one. Even if I know that sigma infinity exists, this equation might have infinitely many solutions in the case when A is not stable. Okay? That is why I do not try this method first here. So here sigma k is A to the k is going to be 1, 0, and I have 0, 1 over 2 to the power k, times sigma 0. Sigma 0 is given as the identity matrix. And I would have A transpose to the power K, but A is diagonal. It really doesn't matter in this case. Transpose really doesn't matter. So I have this one. And let us write the summation plus I from 0 to K minus 1. Remember, we could change the summation variable such that this is A to the I, A to the I like this, and this is going to be, I would have 1, 0, 0, 1 over to the I, and I make a summation variable change here from 0 to K minus 1, this becomes I, as I did before, and I have GQG transpose, which is this matrix, 0, 1, 0, and I would have the matrix transpose. It's a diagonal matrix, it really doesn't, transpose really doesn't matter. 1 over 2 to the I, 0, 0, okay? So now this is going to be, I have all diagonal matrices here. So you see that I can multiply the diagonal elements. That is the only thing that I need to do here. Because multiplication of the diagonal matrices can be found by multiplying the diagonal elements one by one. So I have 1, 0, and I have 1 over 4 to the power K. And plus I from 0 to K minus 1. So here I have multiply the diagonal elements. Again, all of the matrices are diagonal. 1 times 0 times 1, 0, 0, 0. And I would have 1 over 4 to the power I. Okay. So now I'm ready. So this is sigma K. I really do not want to calculate it. Let K go to infinity. In that case, I see that this one is going to remain here, and this is going to go to 0. Sigma infinity is 1, 0, 0, 0, plus all three elements would be equal to 0 here. And the last element is going to be I from 0 to, let me write the result directly here. I from 0 to infinity, 1 over 4 to the power I. This is going to be 1 over 1 minus 1 over 4. By the geometric series conversion, okay? But this is going to be 1, and I have 4 over 3. This is 3 over 4, reverse it, and I have this one. So you see here that in this case, sigma infinity really converges, even if A is not stable. So this really does not violate our theorem, because our theorem really does not say anything about the case when A is not stable. So here I can say, even if A is not stable, sigma infinity exists, and it is actually a positive definite matrix here. Okay? So now I will ask the final question of this lecture, and that is going to be the following. Can I find, so suppose, so I have this implication now. A is stable, implies sigma infinity exists. Suppose that, and I see that the reverse in general is not correct. That means that in order to make sure that the reverse is correct, I need to make more assumptions on the system, okay? In order to be able to make sure that the reverse is correct, I need more assumptions. The stability of A is not really sufficient to make sure that the reverse, actually it's one of the statements. So the current assumptions on the system does not enable us to say that the reverse implication would be correct, okay? What happens, or what would be a condition that I can assume such that this implication turns into a double implication, okay? This becomes an if and only if. I want this to say A is stable if and only if sigma infinity exists. So I want to be able to say the reverse result. When sigma infinity exists, I want to be able to say A is stable under that assumption. That is going to be the topic of the next lecture of this week. And we are going to see that there is a very natural control theoretic condition that we can assume, which would enable us to be able to say that the reverse would also be correct. Here, I see that on this example, I see that the reverse statement is definitely not correct. Sigma infinity exists, but A is not stable. So that condition would definitely not be satisfied by this system. Okay? The condition that we are going to impose on our system is going to be called reachability. So if you have taken control theory courses in your undergraduate or undergraduate studies or your graduate studies, you might have heard the name controllability. When you try to examine the control issues in continuous time systems, the issues of controllability and observability would always appear. In discrete time systems, there are two types of controllabilities. One is called, again, controllability, but it is really a weak condition. It is not a good condition that would give us a lot. And the second condition is called reachability, and it is the proper controllability condition in discrete time systems. Because we are dealing with discrete time systems here, we are going to see that if I assume that the system is actually reachable, that state space representation is actually reachable, in that case I would be able to say that the reverses would be correct as well. And here it's not surprising that this system will not be reachable, because the reverse statement doesn't hold for that system. I will, because in general, when I give the course, even when I give the course 502, I do not talk about discrete time system controllability and observability at all. And actually, I'm not assuming that you have taken the course E502 in this course. As a result, I would like to explain in the next lecture what reachability is. And after explaining reachability, we're going to see that the reachability condition will ensure that this implication turn into a double implication. It will turn into an if and only if statement. And in that case, we would be definitely able to say that when sigma infinity exists, A is stable. When sigma infinity does not exist, A is not stable. And actually, we can say it now. We can say with our theorem that when sigma infinity does not exist, A is not stable. But here, we cannot say with our earlier theorem, we cannot say when sigma infinity exists, A is stable. We will be able to say it if we assume that the system state space representation satisfies some condition called reachability. But that is going to be all for this lecture. Thank you very much for watching. Bye.